Hi, everyone. Thanks for joining us today. My name is Trisha Hamilton, and I'm on the board of the OPWA. For our presentation today, a few things. So your microphones are all muted and your cameras are turned off. As Stephen is giving his presentation, if you have any questions for him, you can add those questions in the Q&A box, which should be on your Zoom screen. After Stephen has gone through his presentation, at the end, we'll go through any questions that we have received. So that would be good. On behalf of OPWA, we would like to welcome everyone who's joined us today, both members and non-members. So OPWA, we're a not-for-profit organization of professional works practitioners, and we're the Ontario chapter of the Canadian Public Works Association and the American Public Works Association. We have over 600 members of public works practitioners that include people employed by the governments, municipalities, consultants, utilities, contractors, and suppliers. We do have two branches set up. So one is in the Niagara region and one is in the West Central branch, as well as the Ottawa Valley branch. So for any non-members who are joining us today, I would encourage you to take a look at our organization and consider joining. Our mission statement is to connect the public works community, and the Ontario Public Works Connects is our monthly program where every month we have a different topic which would be of interest and value to our public works practitioners, which is what we're doing today. So again, I'd encourage you to visit our website to learn more about the upcoming events that we have and the resources available to our members, as well as the benefits of becoming a member. So with that, I'll provide an introduction for Stephen and his presentation today. So Stephen Riley is a senior engineer at Burnside with over 35 years of experience in planning and design of provincial and municipal bridge structures, along with a variety of municipal infrastructure projects. Stephen became the regional manager for Georgian Bay in the fall of 2018 after 19 years as the manager of Burnside's Bridge Design Group. In his role as regional manager, Stephen oversees a broad range of municipal-related service teams, including linear infrastructure, stormwater management, road design, subdivision development review, and bridge design. Stephen represents Burnside as the primary client liaison for Georgian Bay region. So we'll turn that over to Stephen. Thank you so much.
Hello, everybody. Thanks for taking some time today to talk a little bit about bridge inspections. What I hope to do today is to talk about what inspections are, and more importantly, to allow you to get some information that allows you to get more with the information that you're provided by your consultants. So everybody has to do their bridge inspections every couple of years. And so a lot of times we see the reports just going on a shelf, and we hope through this you might learn that there's lots more that you can get out of one. The topics I'd like to talk to today include why do I have to inspect my bridges? What format does it need to be in? Because we see a number of different formats across the province. What is OSIM? What is BCI and how does this help you? And then talking about inspections and how this can lead to maintenance. And then another topic is what can we do for ourselves? And that's going to be a point of discussion where we have to ask ourselves, what are our capabilities with respect to maintenance on bridges? So in terms of why you should inspect your bridges, first and foremost, the legislation, Regulation 10497, says you have to. And what it does, it allows you to identify repairs and the need for any improvements that you might be able to see. It identifies maintenance needs and critical safety issues, and it can assist you in long-term planning. And I often think about it in terms of when you buy a piece of equipment like a snowplow or a dump truck, how much money do you spend on that particular asset? It might cost you $200,000 or $300,000 for the truck, and then every week you're maintaining the truck, you're washing the truck, you're fueling the truck, you're doing oil changes, brakes, all sorts of maintenance. But then you have $30 million of bridge and culvert infrastructure, and how much money do you spend on maintenance on those assets? And most municipalities have a lot more value of bridge assets than they probably are aware of. So there's a regulation. So everybody quick, hurry, read that. Just kidding. The most important part is this part here, which says that every bridge in the province has to be inspected for safety and integrity once in 2 calendar years. So that's kind of the driving force behind why you do it. And then it's what else can you get out of this? So what formats are there? Well, if you're with the MTO, they have their bridge management system, BMS, and that's fundamentally the basis for a lot of other systems. It's a severity and extent criteria. So what that means is that you look at a particular component and you see how severe certain defects might be, and might be light rust, for example. It might mean heavy pitting. It might mean holes, perforations in the steel. So there's a severity of a defect, and then it's to what extent on the component is this defect impacting. There's also discussions in there of performance issues on your bridge. It might take the form of, does your bridge vibrate too much? Is there ongoing settlement? Is there other movements on the bridge that you need to be aware of? And then of course, there's an issue about maintenance, and there's a number of items that are described as maintenance, and you can try to take those up within a short period of time. The OSIM is the Ontario Structural Inspection Manual, and that forms the sort of the backbone of most of the bridge inspections. It's based off of the MTO BMS. It's again the severity and extent criteria. Sometimes we see other municipal driven or consultant driven formats. Depends on the size of the municipality. They may have their own format, and also certain consultants have hybridized and simplified some of the OSIM information for some of their clients. Now, OSIM is the most often used system that's linked to funding, and this is often through the BCI or the Bridge Condition Index. So when we speak about the Bridge Condition Index, we think about it that the conditions for a component of the bridge are either excellent, good, fair, or poor. And the BCI, and you can do it by component, but the way I try to envision it is if you have a blank wall representing a component, if all of the wall is perfectly good or excellent shape, then you get a high BCI. As you start to have a defect that might be, say, the size of a window, you might drop to good or fair condition, and then your BCI goes down as the size of the window gets larger. If the size of the window gets to be the size of a door, you're down into fair or poor, and your BCI declines respectively. So the larger the defect as a percentage of the component, the lower your BCI score goes. Now, it's weighted by the relative value of the component. So if you have, you don't want everything weighted equally. If you have a damaged handrail on a bridge, for example, and its BCI is very low, you don't want that driving the whole score for the bridge. So it's a very lowly rated, ranked BCI. But if that same bridge had problems in low BCI based on a girder, for example, well, it's certainly a much more involved repair process or replacement process. And so its weight in the overall calculation of the BCI is much higher. So again, it ranges from 100 for a brand new bridge is what you want to see. And that's where everything is in excellent condition, all the way down to 0 where everything's in poor condition, but usually by 0, you will have taken some action. Now, the bridge condition index declines over time. Every single bridge will have its own rate of decline. It will depend on such things as your traffic volume, how often and how much you might use road salts, the type of structure, if you have a nice integral abutment bridge, for example, versus a steel girder bridge with old joints. It will have an impact on how quickly your bridge will decline. And each bridge would have its own declining curve that represents its BCI. So what do we do with the BCI once we get it? Well, first of all, it's important to know that the OSIM inspections provide you all the information to calculate the BCI. And so once you have your system of bridges inspected, you'll be able to prioritize your bridges by the lowest BCI might need the most attention, and of course the highest needs the least attention. And then I have to stress this many times. It's not a single point of, you can't just look at your BCI and say, I'm going to do project A first. This is only one input into the planning decision that might go into a bridge rehabilitation or a replacement, but it's a good place to start. The other things you have to think about are the traffic volume, the road geometry, load limits, future growth, history of accidents. All these things have to be considered in addition to bridge priority BCI number. For example, if your lowest bridge is on a very low volume road, you might want to prioritize a bridge that has a higher BCI for replacement if it was to be on a road that has more traffic or potentially more traffic due to future development. So again, BCI is important, but it is only one input into the planning decisions. And this comes down to things such as functional versus structural adequacy. So the BCI will tell us something about the structural adequacy of the bridge, but sometimes, and we just recently did this, we replaced what was a single lane bridge due to the construction of a facility that was going to drive a lot more traffic. It was a manufacturing facility. A lot of people in the local area started to use that particular road, and that bridge needed to be replaced, even though it was probably, in terms of its BCI, 10 or 12th on the list. It was taken to number 1 because it was functionally inadequate rather than structural inadequate. So again, BCI is just one priority, one planning decision, and I always want to stress that point. Earlier, I said that every bridge has its own curve for how it might decline over time. And no two bridges are going to be exactly the same. But the MTO has taken all of their data and they've put together some curves that kind of represent a typical decline for bridges. And this is a curve for a bridge that has an expected lifespan of 75 years, which is the requirement of the bridge code. And this is how you would get that 75 years. You'll see that it starts at 100. There's a decline down to a certain point around 60 where they plan to do a rehab. They can usually rehabilitate bridges to up and around 80, but it's not guaranteed. And then you'd start on the decline back down again, and then you get up to your 75-year design life. So how does this help us at the time when we're doing our bridge inspections and we're calculating our BCI? Well, it allows us to say, you know, if we have a bridge that today has a BCI of 75, we can present that to our clients and say that in X amount of years, they're going to hit a point where they might want to initiate a rehabilitation of that structure. The alternative is to do nothing, and the curve would continue down to Y amount of years when it would be in need of replacement. So it allows them to start to think about when they might initiate a rehab, what service life they're going to get out of it. And so why is this important? Well, if you have 100 structures in your inventory and you just replaced 5 in the last 5 years, so those are easy, and you have 5 that are in poor condition, so you know you're going to do those in the next 5 years. But what about the other 90 some odd bridges? You want to be able to kind of forecast where you're going to have a funding crunch. It might be 30 years from now, you're going to have a whole bunch of bridges that are going to come to the point where they need extensive rehab or replacement. And it's good to know in advance that you're going to have this spike in funding needs so that you can start to plan for it and maybe smooth out some of the spikes by relocating some of the timelines for the rehabs. Now, again, this structure that we inspect here at 75, it's not for sure that next year it will be the next number down. You may find that you flatten out at 75 for a while, or the curve may be steeper. Again, every bridge is different, but this is kind of it's the only tool that we have, and it's the better than the one we don't have before this. So I find this pretty useful, and most of our clients do as well. So when we get into inspections themselves, what are we looking for? Well, there's going to be things that are clearly obvious. There's going to be things that are serious structural defects and potential emergencies that might require the road to be closed, and I've closed several bridges due to this. We might find performance deficiencies where bridges aren't being able to expand and contract, react to the temperatures as they're supposed to. Their movement is restricted. We might find some repair, and we might identify replacement needs for components or the bridge in its entirety. And then we come to maintenance as to whether we can do this in-house or go out to contract. Now I'm going to take a sideline here and talk about that, because it's come up recently with some of our clients that they wanted to develop a system where they would have their own operations folks go through and do all of their bridge maintenance that's engaged or that is identified in their OSIM reports. And we were hired to look at their existing OSIM reports that we didn't do and just go through the maintenance needs that have been identified. And then we sat down with their operational staff and we said, which of these things can you do? And it was kind of an eye-opener for the maintenance staff and the operations folks, because a lot of the things that get flagged in some OSIM reports are beyond the capabilities of most municipalities. We have to remember that this was created for originally by the MTO. And so when you start to look at these are the listings of things that are identified as maintenance in a typical OSIM form. And you start to eliminate some of them pretty quickly, like lift and swing bridge maintenance is a very limited application for that. Bridge cleaning, you can certainly do that with your own staff. And I think if you walk away today with anything, you're going to hear me say the word clean your bridges a million times. Handrail maintenance, you may be able to replace tube rails with your own staff. Most municipalities are not in the business of painting their steel structures. Most municipalities are not in the business of doing deck joint repair other than flushing them out. Very few people are capable of bearing maintenance, structural steel repairs, concrete repairs. This particular municipality said their staff could do horizontal concrete patches on a sidewalk, but they couldn't do anything that was vertical. So it limits what they could do. Timber repairs, again, they weren't particularly geared for that. Bailey Bridge, again, is pretty specific maintenance, and most people don't have that. Animal or pest control, there's certain things that you can do if you don't have rodent traps on your drainage outlets. You might be able to do something there. Surface repair, well, that depends on whether it's concrete repairs or if it's just going to be asphalt. Erosion control is something that a lot of people can do. You can place additional erosion protection in with your own staff. Concrete sealing, depending again whether it's a spray on or roll on. Route and seal of the asphalt is something you're probably going to do with your roads anyway. Deck drainage, and when I say that, it's not just cleaning them out. I'm talking about extending drains, and we'll see that in a bit. And then, of course, erecting or maintaining the hazard signs. When we went through that list with this particular municipality, and they were a medium-sized city in the province, and they realized that they really were not cut out to do a lot of what is described in OSIM as maintenance. And so they had to recalibrate how they were going to do that, what they could do in-house, and decide what they had to contract out. So when we get back to the inspections themselves, and you're going to see some photographs here that I've collected through the years of things that you just shake your head at when you see them. And I don't use any municipal names, just in case anybody is listening. But this is one of those pictures that falls into the stating the obvious. Here, the flanges come completely detached from the web. So, you know, this is certainly not good. Similarly, here's another bridge where you can put your hand through the web at the bearing. So this is also not good. These are just things we've run across. So, you know, beyond the obvious, those kinds of obvious defects where you have large holes or major structural concerns. What else can we tell us? Well, we can find some discussion about what causes some of the defects and what can we do to correct some of these defects in the short term. We can create watch lists, which are things to keep an eye on and watch to see that whether they get worse, and if they're getting worse, how quickly is that happening? And we can identify immediate safety hazards, and we can take steps to prevent certain issues, and we'll touch on that. And we can start to think about repair guidance, where you might engage someone like myself or many of the other consultants to give you guidance on how to repair or do work on your bridges. So in the causes and defects, I've selected a few things to talk about here. This is a very common kind of structure. It's a concrete cast in place T-beam. We see them all over the province. They're very popular. They often have no downspout for their deck drain. Now here someone has kindly put a water bottle in, which isn't really helping anything. But what happens most of the time here is that the water comes through, it runs along the soffit of the bridge or down the inside face of the girder, and it starts to damage the inside face of the girder, and it starts to damage the soffit. And when you have a situation like this, where you have also got low cover to your reinforcing steel, you start to get damage to your soffit, you've got damage to your T-beam, concrete beam on the inside face. This is so common. I see this thousands of times. Just about every concrete T-beam has the same problems to some extent. It's soffit and beam damage. And the solution here is you can extend the drain. You can take a steel spout and extend it down below the bottom of the girder so that the drainage water cannot get on your concrete components. Now this one's probably a little late for that, but if you catch it, you can do this. And it's not just always the case with T-beams. It's any kind of structure that has no drain system that gets below the closest beam. This is a old steel truss bridge, and it is obviously, there's got a buildup of sand and debris over time. A lot of these things were built with angles for tension members that almost act like a cup to hold all this stuff, the sand and debris built up. And of course, if there's sand and salt, you get water, salt in there, you're going to have corrosion of the gusset plates, the corrosion of the tension anchors, corrosion of the inside girders, just a lot of corrosion that comes along with having this material build up on your bridge. I didn't find the picture, but I did come across a steel truss a few years ago that had about 1.5 inches diameter. I'll call it almost a tree, a bush growing in it. It certainly didn't pop up overnight. It took some time for that to grow. And it was obviously clear that they were not maintaining that bridge. So this particular bridge was had to be closed on an emergency basis, and it was immediately repaired so that it could be open for school buses and such. And then it was immediately planned for replacement. And I want you to keep in mind that that happened in about 1996 that we built the new bridge there. Sorry for the old picture, but it tells the story. 1996, this bridge ultimately was replaced. This bridge is the same vintage as the one you just saw, but in this municipality, every single year, the road superintendent went out and washed the bridge. He usually used the fire department, so I don't know whether everybody can do that or not. And later started hiring a bridge contractor to flush the bridges. But they went out and they washed their bridge every single year. And this bridge was built around the same time as the one we just saw a picture of. And I can tell you that this bridge was replaced in 2016. So an additional 20 years of service life was gained simply by washing this bridge. And when this bridge was replaced, it was not, its BCI was still almost 60. And it was basically, they had more traffic volume on the road, and the bridge was becoming functionally inadequate as much as it was structurally inadequate. And rather than spending money on repairs, they elected to replace it. But 20 extra years of service life just by washing the bridge. Another common situation are expansion joints. The idea of expansion joints is exactly as it is, expanding. As the weather gets hot, the bridge wants to get longer. It wants to move back and forth with the joint. When the joint is full of debris like this, sand and debris, it basically can't move. And now it's adding stresses into the bridge that it wasn't designed for. And this stuff, if it stays for too long, it becomes almost like concrete. And so it stops the bridge from moving as it's intended. And you need to make sure that you're cleaning this, because it also, a lot of these joints have a rubber seal in them, and you'll damage the seal, which can cause leaking. And so again, I'm back to my cleaning discussion. You need to flush those joints and do it every year. Again, it buys you service life, and it's easy to do. Here's another joint that's gone a little worse. In this case, it was more of a compression seal type of a joint. In this case, the strip seal was broken, which means the water and the sand are going to get through. It's been partially paved over. We've seen situations where they've paved a bridge deck and just paved right over top of the joint as well. And so now this joint here, the strip seal is damaged. It's leaking, and there's really not a lot you can do here except to replace that joint, or maybe consider eliminating the expansion joint through a major rehabilitation. Now, if you go underneath the bridge like that, you'll see something sometimes like this, where the joint has been leaking, and we have a lot of sand and debris that builds up on the beam seat and on the bottom of the flange of the girders. Of course, it comes along with it, comes the salt and the water, and you start to get corrosion along here. And again, you can see some greenery that has taken root there. And that's because the water, it's getting watered every time it rains, and there's all that dirt to grow in. And this was not, there's not a planter that was planned for this location. So this, again, we go back to, here's another place where you can clean the beam seats, clean those areas, don't let material build up. And this is an easy something that you can do with your own staff. When we talk about watch lists, hazards, and prevention. So in this case, we want to find areas that we can monitor and see how they're performing over time. We can consider areas that we want to consider for future construction or maintenance. We can start to identify them in advance. And again, take action before you have a problem. So one of my favorites is multiplate pipes. Multiplate pipes are pretty common all through the province. And there was a time where many pipe arches, CSPAs, were put in. And there's always, I can almost tell you in advance what the problem is going to be when I walk inside. I have a mantra when I send out my staff to monitor construction of these or inspection. And there's two things I tell them. One is the bolt hole closest to the visible edge should be in the valley of the corrugation. So you can see here, there's the visible edge. There's a bolt closest. Further away are the bolts that are on the crest of the corrugation. Now, this would be true whether you're looking at it from the inside or the outside. The other thing I tell people is, if it's going together easy, it's going together wrong. And the way I say that is the way that these are installed typically is you have a crane holding up the panel, and one end of the panel rests on the outside of the plate that's already, the lower plate that's in place. And so it rests on there, and you can just tighten the bolts up. But the way the plates are manufactured, on the other side of the culvert, to have this arrangement, you have to have the plate on the inside of the lower plate. And that means you have to push it and hold it in place. So you need an extra person. And so again, if it's going together easy, it's going together wrong. So what does the other side look like? And I don't know how many times before I walk into a culvert with a road superintendent, I'll tell him what he's going to see on his pipe arch. And he's going to see this. This is cracking of the bolt holes. And again, you'll see here, the closest bolt is on the crest of the corrugation, and the furthest hole is in this is reverse of what we want to see. And this is one of the results. They found after some time that it's the way the plates are arranged, it's a weaker design in this factor. There's also, it depends so much on the quality of the backfill and how well it's compacted. You'll notice these things are called soil seal structures. The soil is a critical component. And the backfilling of these structures is very, very critical. And it's more critical the sharper your radius. So a round pipe isn't as much of a concern as an ellipse, isn't as much concern as a pipe arch, which is where the majority of these are, where you have the high radiuses, you have poor compaction, and you get this kind of cracking. It's very common. And again, the shape of the structure will dictate this. The pipe arches are by far the worst. Here's an example of, a culvert failure that is a bit of everything. There was bolt hole cracking. There was no head walls at either end. The water was going underneath the culvert, washing out all the support, and it just buckled right up like this. Of course, it had to be replaced. Sometimes if you catch it and you can do a temporary repair. Here's a situation where there was some reinforcing steel that was welded alongside each of those cracks to sort of replicate the steel that was missing. It's a temporary repair, but this particular one bought that municipality 20 more years of service life. So rather than spend the money right away, they were able to extend the life of that culvert. Now, it certainly is safety concerns. You're welding in an enclosed space with galvanizing. It certainly takes specialized equipment and such to do it, but this is a temporary repair that's fairly inexpensive that can bide you some time. If the structure's under a lot of fill, it's going to cost a lot of money to replace. Other things to watch for are ever-growing potholes in places. So here you have a pothole that's on the approach to a bridge that's requiring constant maintenance. The pothole grows over time. Like every spring, your road super comes in and says, this pothole's getting bigger and bigger and bigger. Well, what might be happening? In this particular case, it was a structure that's founded on a pile and lagging foundation system, and the lagging doesn't go below the stream bed. So every year, when the water is rushing through there, it's drawing some of the material out from underneath the lagging and taking it away. And of course, if it goes from the bottom, it sinks in the top. And so your pothole's always growing, and now the benefit is it is a paved surface, so you know that it's happening. In this particular case, it's on a gravel road. And so when they grade it every spring, they don't know that there's anything happening. They just grade it, and they don't notice that there's anything happening. But here you can see again, stream water is taking away the granular material. And you can see that over time, they've tried other bits of fill in here with larger stones. And there's another photo I have that shows where they had a road sign that was thrown into the hole at one point. So with a gravel road, it's less obvious, but this kind of thing should come out in your bridge inspection. In this case, it was time to rebuild that abutment. Another thing is watching your culverts or structures for buildup of debris in the stream. Obviously, this is a problem with it affects the hydraulics. And of course, if you had a really big storm, you're at a greater risk of having a complete washout if your structure's partially or fully obstructed. So you need to make sure you can do that. And this is something you could likely do again with your own staff rather than contract that out. Here's a common situation on a granular road where every year they've graded the road, and graded the road. The road surface is up here now. This concrete is a barrier that used to be about 1.5 feet above the top of the bridge deck. And so they just kept grading it and grading it and grading it. And they didn't really realize that they were burying the barrier system until we got out there and looked at it and said, what is your barrier system? It's under the ground, it's under the road. So we recommended they don't grade anymore. And the best way to do that is to remove the fill and then pave the bridge and the approaches so that you're not likely to grade over top of it. But this is pretty common, and it happens so gradually that nobody really notices that you're filling in parts of your barrier system. And then of course there are places where it is very noticeable, where someone's taken the trouble of building up with sandbags the road approach because they see themselves doing what they shouldn't be doing. But this is a case where it is sometimes noticed and they just do it anyway. This is an example of a safety hazard, a real hazard. In this case, the guide rail is not connected to the structure. So when you connect a guide rail to a structure, what you're doing is making a transition from a flexible guide rail system that in normal applications can deflect about a meter is kind of what they expect. And you'll see with most bridges, as you get closer to the bridge, they add more posts. And what they're doing in that situation is they're adding stiffness to that assembly, and they're making it less and less able to deflect, because the concrete isn't going to deflect at all. So they want to transition from a flexible system on the approach that will guide you back onto the road, making it stiffer as you come to the bridge and connect it. That's the idea, to slowly, gradually increase the stiffness so it won't deflect. In this particular application, you have a system that can deflect up to a meter. So if you happen to hit this and you're a meter off the road, you're going to hit onto this post. And in this case, you'd almost rather take your chances going down the hill into the stream than hitting this post. So this is a very, very significant hazard. There are OPSD standards that allow you to connect to existing barriers with drilling and ways to connect it, and standards for the approaches. This is one of the things we flag as a hazard on many of our bridges. This is worse than not, I think, this is worse than not having a guide rail at all. And like I said, it is a lot more common than you think when you drive around the province. Here's an example of a makeshift retaining wall that was put against an abutment that was designed, sorry for the engineers, designed too short, didn't accommodate the road, and so they had to build something, and it's obviously falling apart. And so this had to be all reinstated. And what happened here, obviously, is that it fell away, it started drawing material, and this became a hazard for bicycles, people walking, and vehicles, obviously, as the retaining wall failure led to erosion and wheel magnets, I call them. So we had to reinstate the walls and the roadway, and then control the drainage, because this can also happen at other structures where you don't have any sort of curbs beyond the end of the structure, and the water just goes around the edge of the barrier wall and erodes your slope right here in the same location. And so it's controlling the drainage. So you may have to go out in some of your structures that have this kind of erosion and add on a little bit of curbing that'll take the drainage further away from the bridge. Again, that's not a big fix, but it can save a lot of problems down the road. And lastly, in terms of get some engineering guidance before you go and tackle some construction. So in this particular case, you'll see that this steel truss has buckled completely. It was a very light truss. It only had angles for the top cord or compression cord. So it was not a very strong or heavy duty truss, but the municipality in question thought that they didn't need to have an engineer. They're just going to hire a contractor to directly replace the bridge deck. And so they did. They hired a contractor, and I know the contractor, and the contractor did a great job putting a nice, thick, heavy concrete deck on it. The problem is, with the heavier deck, the new deck, you're using up the capacity of the truss. The truss has a fixed amount of load it can carry, and that you want to share that with as much live load, so trucks and vehicles, and the lowest amount of dead load. In this case, the contractor put on a nice, heavy, thick deck. And when the township was going to do, they were going to do the road work beyond, and they were bringing a large load of granular material over the bridge to dump on the other side. As they came close to one end, they started to raise the truck bed, increasing the load even more on the back axle. And all of a sudden the truss blew out instantaneously and was ruined. Our advice in advance of doing that would be to do a bridge evaluation and determine what is the capacity of that truss. Can it be repaired with a concrete deck? Would you be better off in this environment with a timber deck that's lighter weight, you can carry more load? So do that engineering up front is going to save you money, because after this happened, then I got a call, and then we went out and redesigned a new superstructure. So they not only spent almost it's going back a few years, but they spent a couple $100,000 to replace this deck, and then they had to redo the whole thing. So, you know, a $10,000 evaluation would have saved them hundreds and something $1,000. So get some engineering assistance before you do that. This is the deck again, and there wasn't a crack in the concrete deck at all. It was, you know, the contractor did a really nice job of something that didn't work. And this picture shows this lump of gravel here, and people ask me, is that the gravel the township was putting on when this buckled? And the answer is no. This gravel was placed there because this gentleman that owns this house continued to use the bridge after it had buckled. So we had to prevent him from doing that. So that is, in summary, what I want to reiterate here today is, when you do your inspections, you can identify urgent needs for immediate action. You can identify areas to watch and for progressive problems. You can identify common defects and simple maintenance measures that you can take with your own staff. And you can identify hazards like that guide rail and how you can take proactive action to repair that before you have an accident. You can save money and extend the service life of your structures. And that wasn't the clear example of that was those two truss pictures, one that was never washed and one that was washed every year, and bought another 20 years of service life out of that. And then of course, you take all the information you get from your bridge inspection, you have your BCIs, and you start to be able to plan for the long term. You can plug that data in with your asset management system, and you can start to progress where you're going to have the need for more money down the road, and you can try to smooth out the peaks and valleys of that demand. So that's kind of all I had for today. I see there's a couple of questions, we'll get to those. So thank you for your time. And like the sign says, this is a shameless plug for our Scenic Cape suspension bridge that I designed about 15 years ago. So that's all I have for right now.
All right, thank you very much, Stephen. I learned a lot about bridges, and I've been on that suspension bridge, and it's gorgeous there. So I appreciate the plug. So if you do have any questions for Stephen, you can add them to the Q&A section of your Zoom bar. We do have a couple of questions that we'll go over first. So one of the questions is, what software exists for creating and managing the bridge degradation curve?
The MTO provided us those particular curves, but just in basically an Excel table. And we just generated ourselves the graphs, and we turned those curves into an equation, and that's what we use in our OSIM forms. We've built that right into our OSIM form, so that as we update our areas and components in our structures, our BCI is changing on the fly as we input the information. So in terms of, I don't know of any other software. I know the one that we use, we created ourselves, and it works for us.
Okay, great. Another question we have, apart from the Stantec BMS, what else is being used in Ontario? Also, considering that only MTO has a dedicated contractors to deal with deficiencies coming out of BMS, which BMS software gives the most value for municipalities?
Well, it's a good question. I don't we don't do a lot of inspections, or we don't do any inspections for the MTO. We're familiar with the BMS because we go to the training for that. Again, we've developed our own internal software for this tracking. When we've gone to other municipalities, we've seen other consultants have developed their own systems. We've seen hybrid systems. I don't know that there is a one system that's better than another. There was previously through MDW, they had an online system that they hoped would gain traction, but it didn't. So I don't know that I'm aware of an overarching system that isn't proprietary to a particular consultant.
Okay. Another question we have, can you elaborate more on inspection of bridge bearings and what to look for in particular?
Yeah, when we look at bridge bearings, what we're looking for are bulging on the side. We're looking for cracks in the bearings. We're looking for rotation of the bearings. So where you might see the one side is thinner or appears to be thinner than the other side. We're looking for deformation. So where it looks like it's being pushed in one direction or another. But when we see that, we have to recognize that if there are definite deformations that are supposed to happen in concert with the changing weather. So you might be looking at deformations that are contrary to what you expect. So if it's a hot summer and you expect the bearing to be pushed slightly towards the ballast wall, but it's the other way, you may have a problem there. When we look at older bridges that have steel plates for bearings, or old rollers, exactly, whether they're seized, whether they can move, whether or not there is any play left in the expansion joint and in the bearings. We see a lot of old trusses where, in fact, it seems like the abutments have rotated in and the bridges are as pushed back as they can go. There is no more room for repair, for movement, I mean. So those are the kinds of things we look at it for bearings, mostly related to their condition, bulging, cracking for laminated ones, distortion, and seized up bearings.
Okay, great. Are there any other questions for Stephen? Okay. All right. I'm not seeing any other questions. So with this presentation, it should be available to the attendees. So you'll be able to have that as a reference. And Stephen has provided his email address there too. So if you want to email Stephen directly with questions, I'm sure he'd be happy to address those. So with that, on behalf of OPWA, I'd like to thank Stephen Riley for his presentation today. And I think we all learned a lot about O&M requirements for bridges. Thank you so much, Stephen.
Thank you for taking time to share with me. Thanks.